which travel in all directions, which travel in all directions with the velocity of light, with the velocity of light. I'm repeating the point. Every point on a given wavefront acts as a source of secondary wavelets which travel in all directions with the velocity of light. Now, what is the second thing he has given? The position of the new wavefront, the position of the new wavefront, the position of the new wavefront at any instant is a surface touching these secondary wavelets, tangentially in the forward direction, tangentially in the forward direction at that instant, forward direction at that instant, right? Now let me just explain what he means by that. See, when I take a source, I told you from the source the light goes in all directions, isn't it? And I said it is a wave, it's a spherical wave. So if I'm taking this point, I have a spherical wave like this of light.
Yes, sir.
From here, if I take these points, act as a secondary source of light. Okay, these points which are there acts as a secondary source of light. So again a spherical wave forms, right? See, this is a source. Here already a spherical wave is formed, right? After some distance, I'm just taking a part of the spherical wave. Clear? Now what Huygens said is each point on that spherical wave acts as a secondary source. If this is your primary source of light, these points acts as a secondary source of light. Now these points again they again get spherical waves across them. These points will act as a secondary light source. So whenever there is a light, again a spherical wave has to come, right? Now, if you join tangentially these secondary waves, you get another spherical wave. Clear?
So when you say wave, you said that it's only like the propagation of energy, right? So how can like energy act as like a secondary source of light over here?
This is an energy, no? So it has some energy. It has some energy. This has some energy. So energy is dissipating in form of spherical waves.
No, so first time, like after the primary source releases the energy, how
See,
can
this
that
is a
energy
candle.
act as a secondary source?
This is a candle. Okay. Now a spherical wave forms across the candle.
Yes, sir.
What Huygens told is, if somebody at that time would have asked, how does a light from here is traveling to this point here, right? So somebody has to tell the propagation of the light, no? So at that time, what Huygens told is, see, from the primary source, let me say there is a mother spherical wave which is coming. Clear? So every point on the mother spherical wave which is there will act as a secondary source. From here again your spherical wave form. Okay, now when you join tangentially all these points, you got the light has moved from this point to this point. Yes. Now again, if you take this, these acts as stationary sources. Again, you have some sources acting like this. Now again, connect them. So the light has started from here, it came to here, here, and here. So this is how your light wave is propagating. This is what Huygens has given. Clear? Now, this is okay. This is a theoretical explanation of what Huygens has said, isn't it? Now we have to quantitatively prove this. Mathematically, I should be able to prove this. In physics, until and unless you prove something experimentally, it remains like a theory. That's the difference between theory and law. That's why we say Newton's law of gravity, not Newton's theory of gravity. Clear? Now, in your 10th standard, when you have studied something called as reflection and refraction. Isn't it?
Yes.
Law of reflection, law of refraction. Law of reflection, incident ray, when it comes falls, it will make the same angle and reflect into the same medium.
Yeah.
All in the same plane.
Exactly. Next, the incident ray and the reflector ray are all in the same plane.
Yeah. Yes.
These are two laws which you have studied in.
So there's a third law also.
Sine of angle of incidence to the sine of
Yeah.
That I already told in first point. Anyhow. Okay, third one is angle of incident is equal to angle of reflection. Good.
Yeah.
I'm very happy you remember something from your 10th standard.
We have to
Now
remember.
refraction is given by Snell. This is called as Snell's law. Now when I say light is a wave, only if I can explain my reflection and refraction, then only I can say that yes, light has wave nature, right? See, if your total laws are changing whenever light is changing, is it true? Will it become scientific?
No, sir.
So whether I am in your class, whether I'm in my house, whether I'm at my parents' house or in-laws' house, I will be same, right? So whether light is a wave, whether light is a particle, it does not matter. It should satisfy all the laws which are there. Correct? Now let us see if your wave nature of light can give you a refraction. Put your heading as refraction of plane wave. Right?
What's the definition of wavefront?
Huh?
What is the definition of wavefront?
One second. Just a second. You did not. I told you the wavelength definition and Huygens principle I was telling you. Anyhow, take it down. Wavefront is defined as the locus of all points the locus of all points locus of all points where the wave has same phase, where the wave has same phase.
Sir, FAC or PHAC?
Phase, phase. Again, you're having the same. Now let us try to explain the refraction of a plane wave. So we will see whether Snell's law is applicable for light if light is behaving like a wave. For that, I'm taking a wave which is coming in this fashion. That is, your spherical wave is something like this. Understood? See this one. This is your spherical wave. Okay? Clear?
Yes, sir.
This is your angle of incidence. Right?
Yes.
So this I'll take it as some aid. This I'll take it as some medium. Okay. So a spherical wave is coming from your aid at some angle, and then this part I'll take this point as A, this point as B. Okay. I am assuming the spherical wave. See, you may ask me, sir, why don't you take a spherical wave something like this? Correct? Why I am taking a spherical wave in this direction is if I can prove at some angle, it is true for every angle.
Yes.
So that's why in physics, what we will do is we'll take the difficult task and we'll prove that, and we say this is applicable for everything in every case. Now this is your wave, spherical wave. Now I'm going to draw a normal here, and your wave will go like this, right? Now this point, when this point has reached this point, I will tell my wave is something like this. Understand? Spherical wave, no. If this is like this, so when this point goes to this point, let me say this point has reached this point. This I will call it as C. This I will call it as D. This angle is angle of refraction. Isn't it? Clear? Now we know that the velocity of a wave will change whenever there is a medium change.
Yes, sir.
Right?
Yes, sir.
So how we define the refractive index? How we define the refractive index given by mu? mu, mu, okay. So mu is equal to speed of light in vacuum divided by speed of light in medium. Now tell me, how much distance did the wave B to C has traveled in time t? In time t, distance traveled by BC is how much?
Well,
V
V
naught
not into time.
into T. Fantastic. V naught into T. V naught into T. Right?
Yes,
At
sir.
the same time t, the distance traveled by the wave from A to D is
VM into
Give me
T.
the T.
Vm into T. Clear?
Yes, sir.
Now I am considering my triangle ABC, right? If this is I, then this angle will be I.
Yes, sir.
Amma, please understand. This line with this line is making an angle theta, then this line's perpendicular
It
with
is
this line's
perpendicular with the
perpendicular
theta.
will make the same angle. So this
Yes,
is
sir.
I. So in triangle ABC, can you tell me what is sine I?
BC by AC.
Fantastic. Right? Now, triangle ABC, sine R. Okay, now see, this line with this line is making angle R. So this line's perpendicular I am drawing. This line perpendicular make the same angle. Tangent means this is 90.
Yes,
Yes,
sir.
sir.
Now tell me what is your sine
AD by
AD
AC.
by AC.
By AC.
Correct?
Yes, sir.
But what is BC? V naught T divided by AC. What is AD?
V
VMT
by
divided by AC. Now tell me, AC you can remove, right?
Yes,
So
sir.
from this, sine I divided by sine R is equal to V naught divided by Vm.
Which is mu.
Exactly. Understood? Now see what happens. This is a very fantastic equation. Now tell me, if your light ray is going from rarer medium to denser medium, air is a rarer medium, isn't it? And this medium is a denser medium. Okay. So if your I is greater than R, I is greater than, if I is great, put your case 1. case 1, if I is greater than R, what happens to my V naught and Vm, which is greater?
V naught is greater.
Correct. Why so doubt?
Yes, sir. The voice is greater.
V naught is greater than Vm.
Yes, sir.
So that means whenever the light is entering from A into a denser medium, your velocity decreases. And it is vice versa. Whenever your light wave is going from denser medium to rarer medium, your velocity increases. So case 1, if I is greater than R, V naught is greater than Vm. If I is less than R, your V naught is less than Vm. Clear? So, if light is behaving like a wave, we have proved your Snell's law. Clear? Now, if you further, if you take the diagram correctly, see, because ray optics, wave optics, your diagram should be half the page of your book clearly drawn. Each and every ray has to be clearly drawn. Okay? Shall I go to the next one?
1 minute.
Shall I go to the next one?
Yes, yes, sir.
Now see, the same thing. Instead of taking the medium 1 as A, if I take it as medium 1 and medium 2, right? I'm just taking it as medium 1 and I'm taking it as medium 2. Medium 1